In the previous example, we cut a member at some angle and noted that the average, normal, and average shear stress depends on this angle. If we look at the member in a two-dimensional system, we can define the following. The magnitude of the normal internal reactionary force, Rn, is equal to the magnitude of the internal reactionary force R times cosine theta. The transverse, or tangential component of the internal reactionary force, Rt, would be equal to R sine theta, and the shear area would be equal to the cross-sectional area per cosine theta. Therefore, we can redefine our average, normal, and average shear stress based on theta. First, we'll look at average normal stress. Average normal stress is Rn per An, where Rn is R cosine theta and An is A per cosine theta. This gives the quantity R cosine squared theta per the cross-sectional area, which can be expressed as R times the quantity 1 plus cosine 2 theta per 2 times the cross-sectional area. Average shear stress is expressed as Rt, which is the transverse internal reactionary force per An. Rt is equal to R sine theta, and An is A per cosine theta. This is equal to R sine theta cosine theta per the cross-sectional area, which is equal to R sine 2 theta per 2A. To see this in application, let's consider two pieces of wood that are glued together at a scarf joint. Our scarf joint is measured 40 degrees above the horizontal plane. A load of 2,400 newtons is applied to both ends of the system. The wood structure has a cross-sectional area of 800 centimeters squared, and we need to determine the average normal and shear stress in the glued joint. To start, recall the angle theta is measured with respect to the vertical direction. Thus, we subtract 40 degrees from 90 degrees to get theta equal to 50 degrees. We can solve for normal stress based upon the normal force Rn and the area An. That is, the average normal stress will be Rn per An, which is R cosine theta per A per cosine theta. And this is equal to R cosine squared theta per A. When we substitute in values, the internal reactionary force is going to be 2,400 newtons. The cross-sectional area is 0.08 meters squared, and cosine theta gives us a value of 0.413, which gives the average normal stress to be equal to 12.4 kilopascal. The average shear stress is equal to Rt per An, where Rt equals R cosine theta and An equals A per cosine theta. This simplifies to R sine theta cosine theta per A, or R sine 2 theta per 2A. Substituting in our values, we have 2,400 times the sine of 100 degrees per 2 times 0.08 meters squared, which gives 14.772 kilopascals for shear stress. With this in mind, let's reconsider example 1, but instead we'll determine the maximum average normal and shear stress existing in the axially loaded member and what angle theta these occur at. To find this, we can plot our average shear stress and our average normal stress versus theta from 0 to 180 degrees in MATLAB. We'll define theta, then we use our equation for average normal stress on an inclined plane to define sigma as a function of theta. We use the equation for shear stress to define tau as a function of theta. And lastly, we plot these values on a graph. If we look at the average shear stress, shown by the blue line, we can see the maximum values occur when theta is equal to 0 or 180 degrees. So, when the plane is mutually orthogonal to the axis that defines the center line of the member, normal stress is maximized and is equal to R per A. Looking at the average shear stress line in red, we see the maximum occurs when theta is equal to 45 or 135 degrees. When this occurs, the maximum shear stress is equal to R per 2A. Now that we know the max shear stress occurs when theta equals 45 or 135 degrees, we can use the equation tau max equals R per 2A. Our equation becomes 500 newtons per 2 times 9.07 e to the minus 5 meters squared, which gives the max shear stress of 2.76 megapascals. The maximum average normal stress occurs at 0 or 180 degrees, and we'll use the equation R per A. Our equation becomes 500 newtons per 9.07 e to the minus 5 meters squared, which gives the max average normal stress equal to 5.513 megapascals. Note that the max average shear stress is equal to 1/2 the maximum average normal stress.